Hi everyone to another lecture at Physics Latam. Today we have the fifth and final lecture by Melissa Liu about remodeling conjecture with descendants. Please go ahead, Melissa.
Oh, thank you very much for the introduction. Yeah, and thank you so much for having me again. So today is the last lecture. So since it has been a while, so let me remind you the setup. So we are going to talk. So the remodeling conjecture. Shut. Renew. Is a version of all genus mirror symmetry. So we have, so the mirror symmetry is supposed to relate a model defined in terms of symplectic geometry to B model defined in terms of complex geometry. In the remodeling conjecture, the A model is some symplectic toric Claviel three manifold or three orbifold. And the B model, there's a three-dimensional B model, but last time we have seen that in the remodeling conjecture, the B model has been remodeled and it has been reduced to a theory on the mirror curve. So CQ, so this is the mirror curve. So it's determined by the original Claviel three manifold or three orbifold. It is fine curve in C star 2 and depending on some complex parameters. So P is the number of the extended Kähler parameters of the original toric Claviel threefold. So it's shown. So on the A model, so the remodeling on the A model, we have FGX. So these are closed Gromov-Witten generating function of Gina G closed Gromov-Witten invariance of X. So that's the closed string sector. So we also have the open string sector. So this is open Gromov-Witten invariance of the pair X and LF. So this L is the so-called frame Agnagi-Vafa Lagrangian brane. So here framing is some integer. And then this is supposed to relate it to, so we have so this is essentially y dx, and this is some fundamental Marlborough bidifferential of the second kind. And from this data, and this is there's some choice, but the choice is also determined by the original A model geometry. So from here, so we one can define recursively the check Horrington topological recursion invariance. And the remodeling conjecture should relate. So for the open sector, so this is n is greater than 0. And the closed string sector should be related to omega g0. So yeah, so that's the setup. So today we are going to be more precise. So on the A model, we are going to, I'll first summarize what kind of A model invariance we will have. So first we will have some descendant, which is of this shape. And then we have open invariant. So we will define this generating function precisely. And finally, so this is for the descendant, we have the following. So there's something which is called epsilon 1 epsilon n is in K plus. So we will define this so-called bond. This is case theory of case theory. Hello?
Hi, Melissa. How can I help?
Oh, sorry.
No need to apologize.
I finished it. Very funny.
So case theory, so this case theory of certain case theory of sheaves with bounded below support. And for this, we are going to, so we have defined certain like generating function depending on G and N, and also input Z1 to N. So you can think this as, because this is like count holomorphic curves with, so the second open Gromov-Witten invariance. This count holomorphic curves with Lagrangian boundary conditions. So this is like A-type boundary conditions. But the descendant invariant we will define is like we have B-type boundary conditions. So the boundary conditions are given by some coherent sheaves with a bounded below support. But this invariant only depends on its K-series class. So that's the A model. And the B model correspond to descendant, we have this omega GN. And correspond to the open invariant, we have the B model version of FGN. And it will depend on Q and the corresponding B model invariant. And finally, so we will have the following. So we will have some, if we have gamma 1 to gamma n, actually, sorry. Actually, we want to have some equivariant version. So here T is the Calabi-Yau torus. So here, gamma 1 to gamma n corresponding to the T equivariant version, it will be some gamma 1 to gamma n. So these are C tilde Q relative to X with Z coefficient. So what is the C tilde Q? So recall that CQ is a curve defined by equation in C star 2. Let's take the universal cover C2 and then look at the pre-image. So that's C tilde Q. So the, yeah, so then, so this is the, so I write A because these are the correlator defined in the A model, but with B-type boundary conditions. So now in the on the B model side, so this gamma 1 to gamma n, they are just represented by just real one-dimensional curves in this cover of the mirror curve. So they are in particular Lagrangian cycles in the C tilde Q. So this is given by the following. Oh, I need more space. So on the B model, for the third case, like to state our version of remodeling conjecture with descendants. On the B model side, we insert this actually A cycles. So recall that omega, so this is the whole, omega GMPN is a meromorphic form. Meromorphic symmetric form on C1 to C, and then we can pull back into the cover. So the descendant version will of the remodeling conjecture will take the following shape. So there's a mirror map. So let me call there's also a non-equivariant version, but equivariant version send to this H1. So the descendant version looks like this. Yeah, up to open and let's say, so we have a mirror map between this mapping B type cycles to A type cycle. There's also a mirror map between variable, open, close. Okay, so that's the shape of the, so this correspondence. So that's an overview. So then I want to go into more details of these three versions of all genus mirror symmetry. So let's start with the A model. We need to, so first, so we consider U1, UN, where each UJ, so it's a series of Z where UJA, each UJA is, I'll say this H. So now let's take the big torus. So here HT, so recall that T is the three-dimensional torus acting on our toric Calabi-Yau 3 manifold or 3 orbifold. That RT denote the equivariant cohomology of a point. For now, let's say rational coefficients. Later, we will do complex coefficient. And then let ST be the fractional field of RT. So this HT is the T equivariant Chen-Ran cohomology of X, which we defined last time. And so it's a module over this RT, and we tensor by the fractional field. So recall that we have this notation. So let me slightly change the notation. So So last time we defined this correlators. These are descendant equivariant Gromov-Witten invariants. So the double bracket means that we sum over degree. So this is the effective curve class. And we also sum over, so we also take tau to be some 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 arbitrary insertion of some second Cherenkov cohomology of X. Yeah, so this is the notation. So now, this is defined to be, so recall that each uj is a series, is a series, is a power series in Z. So this is, so the definition of this correlator is just you just insert so we can expand it in terms of yeah, so this defines this generating function. It's a generating function of for fixed Gn. This is a generating function of genus G descendant Gromov genus G equivariant T equivariant Gromov-Witten invariant of our target Calabi-Yau 3 orbifold with n insertions. So this is the definition. Okay, so now there's a theorem. So for the orbifold case, it's due to Zheng Yuzhong. So there's a graph sum formula for this. I will not define the formula explicitly, but it's of the following shape. So it's a sum over, I should say, for each So if we fix Gn, and also we have this target, then for each Gn, there's a set of finally many stable graphs with labels, with certain labels. And I will say more about the weights. Is each graph, each labeled graph, each decorated graph is assigned certain weight. So there's a graph sum formula. So maybe I can say the following. So it's of the following form. So there's some weight depending on V together with the labeling. And similarly, the edges are also decorated with extra data, but this will depend on those extra data. So these are like some dilaton leaves. And then we have this LJU. So this LJU, these are the open, so this is called, we call it descendant leaves, J from 1 to N. So for now, we only need to say the following. So the weights of the vertices, edges, and the dilaton leaves, so they depends on a variable Q and tau. So the J's descendant leaf depends on Q tau and the insertion. Yeah, so we have defined this to summarize. So first we define this descendant generating function of descendant invariance, and we have a graph sum formula. So secondly, let's look at open invariance. So in addition to this variables tau and q, there are open string variable x1 to xn. So I'll write it as follows. We sum over, so we fix in g and n. So we sum over mu1, mu n. These are like winding numbers. So these are supposed to be a generating function count a holomorphic curve with holomorphic from border Riemann surfaces with G handles and n holes. And we need to sum over all the homology class of the relative homology class of the curve, and also the class of boundary circles. So recall that if we have a map from this to X bounded by L, so the boundary are R1 to Rn, the restriction to Ri gives some element in pi 1L. In general, RL is homotopic. So L is a homotopic to a circle homotopy to a circle times B mu M, the classifying space of cyclic group of order M. So pi 1L is like isomorphic to Z, and let's say additively pi 1 of mu M just. And so this gives us some class. So for each, this gives us class U. So let me write this J, mu J K J. So mu J is a positive, this is a positive integer, and K1 to Kn are element in Z mod MZ. And we have this, so this also depends on framing. So today I'll write it in this way. So here, so here is a generating function of open invariance when you fix the winding numbers and this monodromies. But one needs to sum over, when we fix this, and we sum over the closed degrees. And sum over all possible insertion in the interior. Oh, sorry, I should say, so this depend on G. So this is G. Oh, yeah, let me write it in this way. D is yeah, so this we sum over all the possible degrees and all the possible for the fixed winding, all the possible degrees with this fixed winding and monodromies, and we also sum over all possible number of insertions in the interior. So that is this. So now actually there's a so now we can actually compute. Oh, so I also want to say that so we can compute it by, so last time we have defined it in terms of some equivalent localization on moduli space of maps from border Riemann surfaces to the target with boundary conditions in L with this topological data of the map. So we recall that we computed by using the compact Labial torus TR prime, because this is the torus which will preserve this Lagrangian, so its action, so it acts on this moduli spaces. So this is the maxima torus of the so-called Labial torus. Yeah, so we can compute it by using the compact torus, and but then after that we specialize to the framing torus, one-dimensional framing torus. So this invariance will depend on the framing. But when we compute it, actually we can relate this to the descendant Gromov-Witten invariance in part one as follows. So it turns out that we have the following. So FGN X relate to the descendant Gromov-Witten invariance U1, UN, X as follows. So first we introduce the notation. So this takes, so this will take value in S. So this has, this takes values. So this is a functions on closed string variables. So this is a function of this infinite many variables uj a, j from 1 to n, a from 0 to a is any non-negative integer. And depend on like this closed string variable. So this is like Novikov variables, which keeps track of the effective curve classes, and this is some insertion. Now the formula will be more general in part 1, but today we restrict the insertion to just in H2. Yeah, and takes values in the fractional field in general. So then we can restrict it to the like for T prime. So then this will be Q1, Q2, and this sent U3 to minus U1 minus U2. And then there's also the framing torus, which is just one variable, say U. And this is send U1 to U and U2 to FU. So then, so we introduce this notation that, so under this, so we can restrict this to the smaller torus, and it will depend on fewer equilibrium parameters. So we call this T prime, or even XTF. So this is the notation. Okay, so now let's go back. So what's its relation? So recall that this XL. Oh, yeah, so actually let me call this, oh yes, right. Sorry, XLF Q tau X1 hat Xn hat. So this actually is equal to, so after this localization and using T prime and specialized to the framing torus. And recall that we choose the, so when we choose, when we specialize to the Calabi-Yau torus, it will be still well defined. We will not have any. So, so this is well defined also when we choose a nice framing torus, such that this is the specialization is still well defined, then it can be related as follows. So where uj, oh, okay, so let me put in this way. So here you when you do localization, so this uj, so each uj, uja, so it's in this before the specialization is in this, so recall that this is T equivariant chain-rank cohomology of X and tensor with the fractional field. So over this, so this has some basis. So let me call this, so this has a, after this localization, so this has a basis. Let's see. So where this sigma is so it has one-to-one correspondence with the torus fixed point. But so because we are in a like general toric Calabi-Yau 3 orbifold, so this fixed point might be stacky. So it is so G sigma is some finite group, and then this alpha is a character of this finite abelian group. So they have the same cardinality. Yeah, so over this is a like vector space over ST, and yeah, and this is a basis. So in particular, so under this, we can write UJA to be some UJA sigma alpha. And there's a sigma. So for alpha, okay, so here is this. And now let's see. So our Lagrangian is in some one-dimensional orbit, and so our Lagrangian intersect a one-dimensional orbit in the toric Calabi-Yau 3 orbifold. We assume that the coarse moduli of this orbit is of this orbit one-dimensional orbit closure is a complex line. So it has a unique fixed point. This is P sigma. And we call this, so this G0 to be the G sigma. So this Lagrangian picks up a unique fixed point. And then to state the, so for this fixed L, so if fixed L, we fix this P sigma together with this fixed one-dimensional orbit. And then the generic stabilizer is mu m in general. So this Lagrangian, so it's a manifold outside the circle, but along the circle, this circle is B mu m. So with this setup, so given L, there exists explicit function so its power series depend on for each alpha in the, which is a character. So it depends on one variable z and x tilde another variable tilde, and it takes values in the Cherenkov cohomology of BZ mu. So which is, sorry, so let me do it over C. Yeah, so here K is mod M. So there's some very explicit expression depending on the geometry, such that the following is true. So with all this preparation, so this is related to the descendant Gromov-Witten invariance in part one in the following way. So first we specialize to the framing torus, the one-dimensional torus. And then we need to specialize this uj. So it's, so as we have seen that each uj is so the specialization is the following. So where u sigma alpha z is equal to this, but very explicit z x tilde j. If well, if sigma is equal to sigma 0 and is 0 otherwise. Oh, so maybe what so I will state the, So you see, we actually, the generating function, this open Gromov witten invariance is related to like the descendant Gromov witten invariance in part 1 in this way. You specialize this, and then now you specialize to this. So now this, because this will depend, so this will depend on you. So yeah, so it will depend on x tilde j in this way. So then as a corollary, you will have the following. Yeah, so this probably can be called some oh, theorem. So it's from definition and localization calculation. So the corollary is the graph sum. So this f gn yeah, actually I should always assume this because the formula of the stable case. Yeah, so for the stable case, we have a sum over stable graphs. So this is sum over the same graph as in part 1. But then we have so the weights are different. So I call it open weights. So where this open weights, it's also so we need to have so each decorated graph, it has certain weight, and weight is like product of contribution from vertices, and this weight, each vertex, the weight of each vertex depends on the decorations, and also the weight of edges. So now there's this, so here, so this depends on tau q, and I also, yeah, I should show equivalent variable, and so it's obtained by in part 1, and like the specialization of like the framing torus inside the big torus. Yeah, so and then LJO is obtained, it is equal to the this is equal to LJU, the descendant leaf with this specialization. So this is equal to the explicitly given xj. So this depends on so for the j's insertion, we replace by the variable xj tilde. So if sigma is the 3-cone corresponding to the fixed point determined by the Lagrangian and 0 otherwise. So now this depends on not only the closed string parameter, but also the j's leaf depend on the j's open string parameter. And also it takes values in the so I wonder if I should take a break now. So so in the first half, we introduced the we introduced generating function of descendant Gromov-Witten invariance and generating function of open Gromov-Witten invariance, and they have so when 2g minus 2 plus n is greater than 0, there's a graph sum formula. Okay, so now let's do the descendant. So let epsilon 1. Oh, so first I want to introduce something. So introduce this, this is essentially Iritani gamma class. So recall that, so the Cherran cohomology of X. So now we are going to use the T prime equivariant Cherran cohomology of X. So it's a sum over like, so this is, so recall that the initial inertia stack of X has a connected component. And then as a graded vector space, this is direct sum of T equivariant of XV, and then maybe so shifted by twice of the h, shifted by twice of the h of this. Yeah. Okay, so then so this 1v is like the unit here. So because of the shifting, it has degree 2. And also z has degree, so z has degree 2. Yeah, so this total degree is 3, is 6. Cohort. And then we have sum of a product. Yeah, so here di is the, recall that this is or toric. This is a GIT quotient of some like the semi-stable locus by some gauge group. And then, so here we have coordinates z1 up to zp plus 3. And then di, so this ci equals 0 is some define some like toric divisor in here. So then this di is the T prime equivariant Poincare dual. So yeah, so this depends, this explain this, and also this CIV is so because now so V correspond to some element GV in the gauge group, and it acts on ZI by weight exponential 2 pi I. Oh, sorry, too many i's. Let me call it J. DJ 2 pi I CJ yeah, okay, let me still call it ICI. So then I account the ice coordinate by multiplication by so yeah, so it's a fractional number. So this explains this gamma class, but in any case, it just takes value in the like Chen-Ryan equivariant cohomology, and also we modify by this z such that it's like degree 6. So that's a gamma class. It just depends. Some class depends on the toric Calabi-Yau threefolds, and also there's some modified Chen character. So there's some so it's a sum over different components. So yeah, it satisfies the usual like additive property. And so we only need to define for line bundles. Oh, so any line bundle, T equivariant line bundles is of this form, where Ri is some integer. let me just say sum over. Okay. So, oh, okay. So finally, so we have this kappa, and there's a similar, yeah. So similarly, if you have a bounded above or below, it will be a map from bounded above or below case theory to bounded above or below, yeah, cohomology. So if so, then this, yeah, this will be, oh, in, so then we define, so given, so we define, if we have this, take some equivalent case theory class, and we can define this. So this is just defined to be, with our notation, is Z1. Um, oh, so sorry, this is indeed kappa, and this is K, kappa T prime. So this, we use the two-dimensional Calabi-Yau torus. So then from this expression, and it is from the definition, we see that this is just given by the follow. So first you consider U1 to UN, and you let UJZ to be kappa T epsilon 1, Z1, Z1 plus Z, right, from definition. So then, therefore, we also have a graph sum formula. So then, maybe I'll say corollary of the graph sum formula. This is, so now, yeah, let's kappa maybe for case theoretic. So then this weight, again, we will have, for each decorated graph, so we will contribution from vertices, edges, and dilaton leaves. So now we have this so you see that again, this so they depend on so this uj, this is so we have this, and then so we see that basically we just take the graph, some formula of Zhengli's graph, some formula, and then we replace the leaf. So this depend on tau q as before, and also some equivalent variables, and obtained by this ways in part one, and also maybe specialization of the Calabi-Yau torus and LJ kappa. So now let's call it case theoretic leaf. So so we know that we should do the following. The descendant leaf in part one, and let UJZ be kappa T prime. Oh yeah, actually I should emphasize the dependent, because this depends on Z, right? And so now for the, so we need to specialize to Z1 up to Zn. So so for Zj, so for the Uj we specialize to, sorry, so for UJZ we specialize to like the J's yeah, J's K-series class, the K-series class of a B-type brain, and ZJ plus Z. Okay. So that's the, so then for the B model, so we have, the first is omega GN. So fortunately people, so this ANA, and we use, so we have omega GN is again 2G minus 2 plus N greater than 0. So the first part is like omega GN is sum over, so this the same graph, but it's like the B model weight. So it's B model, so it's W check. So yeah, so it's the same. Yeah, so we have the exactly the same set of like decorated graph, but the weights are determined by the like data of B model on the mirror curve. So yeah, the B model version, so everything comes with check. So here, so this depends on the B model coordinate, so it's like little q. And LJ is some meromorphic one form. Oh, sorry, this is actually U. So the LJ U is some LJ depending on some decoration. So this is some one form on the mirror curve. Oh. And then, so then the mirror, so there's a, so the mirror symmetry statement says, if you take U1, UN, so this is on the A model. So, and you let this, so there's some, yeah, precise specialization between U and theta. And you also let Q to be equal to 1. So this is equal to the, equal to omega GN. So the, yeah, so the proof is basically the so it's like by so so this is, so this part is in the previous paper. We prove this using the genus zero mirror theorem for toric orbifold. So CCIT and also Shen Kong Fan Li and Kim. but we also need to do some work because the original Gina zero mirror theorem, in the original mirror theorem, the B model is the three-dimensional Landau-Ginzburg model. So, so maybe we need to do some dimensional reduction argument. So that's the, yeah, that's the first. So the first, okay, so the secondly, we have this B model. So let's first, yeah, so let's focus on the stable case. So we have graph sum. So we have the B model. Oh, so Q is equal to 1. Also, there's a mirror map, closed mirror map, relating tau on the A model side and Q on the B model side. So now so now in the B model, we have x1 hat to x hat. So then this is summation L1 to Ln in so recall that so on the A model side, we have some Lagrangian, so we fix some legs. So this will correspond to, so if this circle is like circle times B mu M, this will correspond to exactly M punctures, and then we have this. So then we have rho 0 up to rho M minus 1. So we pull back, and then using the nice coordinate in this P1. And then, so we get some power series in little q and x1 hat to xn hat. So, but the thing is, because we have a graph sum formula for omega gn, we can plug in the graph sum formula. So we get the graph sum formula. So this is like the open weights. So for the open, yeah, similarly we have So then this Lj omega, we should depends on qxj, and it's oh, sorry, on the B model, the coordinate are x1 and x hat. So we should, so this is expand. So it's obtained by expand this one forms. So the one form in the B model. So this is a B model open leaf near the M punctures. Yeah, take the undivided derivatives. So then, so you see that this, so we already identified this. So then we only need to identify, we have already identified the we have already identified the so we have already identified the like, and yeah, dilaton leaves in the first part. So then, so the A model, so this A model open leaf and the B model open leaf, so they are identified, so this identified using genus 0 open mirror theorem, basically relate F0 and F0 disk invariant. So this was proved by so this is the orbifold case. Okay, so finally, so the part 3, we have Z. So if we get some 1 cycles, so this is given by P1 in gamma 1. So this is the higher loop version of the oscillate integral. So now this will depend on also variables Z1 to Zn. So this depends on like little q and Z1 to Zn. And then we plug in the graph sum formula for omega gn in part 1, right? So this has a graph sum formula. Oh, so maybe I should say that the theorem so this is there are statements for unstable version 2. So under open close mirror map. Okay, so so that's the so now finally so we get this and we have a graph sum formula. So this B model, I'll say like case theoretic. So here, so again we have this and then we have the B model case theoretic. Case theoretic leaf. So then the B model case theoretic leaf is actually given by this depending on LJ. Sorry, so we actually so this is the theorem of Bohan Fang and Song Yuan, Zheng Yizong, and myself. First, we have a like genus 0 version, which is the so using this we show that so this there's a mirror map. We show that yeah, the case theoretic A model leaf and B model leaf coincide. So then we get this version of descendant, like remodeling conjecture with descendant. So we have this oh, here I should say it's the so this is the equivariant version of this map. So then we define this GN and then we have so this is equal to so under the mirror map, which relate tau on the A model side and Q in the B model side. And then we also have mirror map between the brain, and we expect it should be consistent with some version of homological mirror symmetry. Okay, so yeah, so that's all. Thank you so much.